Okay, in lesson 7.2 and kind of going forward, we're going to focus chapter 7 a little bit more on quadrilaterals. And so the first quadrilateral we're going to focus in on is a parallelogram. So in our warm up here, we have kind of a similar problem to what we saw a couple chapters ago with triangles. Let's go ahead and take a moment, pause this, try this in your notes. What I'm going to do as you do that is mark what we have to see what's going on here in the right hand column. So we are given that MN is congruent to PO, and then we are also given that NO is congruent to MP. So that's what's in our given. The next one is we have NP is congruent to itself, and hopefully we all remember that's by the reflexive property of equality. Anytime you see something is equal to itself. Now with all of our markings on our two triangles, we can clearly see that these two triangles are congruent by side-side-side congruence. Now what you'll see in parallelograms is that we'll be using some of these properties of parallel lines and some properties of congruent triangles again. So be ready for those shortcuts. Remember, we had side angle side, we had side side side, we had hypotenuse leg only in right triangles, we had angle side angle, and lastly we had angle angle side. So be ready for those. Also, with two parallel lines and a transversal, we had some of these relationships. Hopefully you guys remember a lot of those. Okay, we had some warm-up problems on our homework, but we remember hopefully like 1 and 5, those are corresponding and they are congruent. 3 and 6 are alternate interior, those are also congruent. And then we have alternate exterior, 1 and 8, that are congruent. And then the last relationship, and we'll use it again today, is consecutive interior, and those aren't congruent, but those are supplementary. So now that we've kind of got that recap out of the way, hopefully we can tie these into some of the properties of parallelograms. Again, make sure you pause to get your theorems down, your pictures down, get really good notes down. That way, if we can use those on a quiz, we are ready for them. So the two big things, we're going to use properties to find side lengths and angles of parallelograms, and then we'll use some properties of parallelograms in the coordinate plane. So what we need to start off with is, first of all, the definition of a parallelogram, and it's very simple. It's both pairs of opposite sides are parallel. So there's nothing to do with the side lengths. We're going to learn something going forward, though, about those. There's nothing to do with angles specifically. Again, those have properties that we get, but the definition of parallelograms is both pairs of opposite sides are parallel. So the first set of theorems that we have to do, like I said, with sides and angles. So first of all, opposite sides in a parallelogram are always congruent. We will also see converse ones in this chapter as well, so be prepared for that. So if you see opposite sides congruent, so if the quadrilateral is a parallelogram, then opposite sides are congruent. The next statement says, if the quadrilateral is a parallelogram, then opposite angles are also congruent. So again, we know both of those things are true every time we have a parallelogram. So proof of opposite sides being parallel, again, what we end up doing is using some definitions of triangles. So again, our first statement in these is always given. And I tried to set these up so that they wouldn't be too terribly tough. Through any 2 points, there exists exactly one line. That's just the definition of a line. But in there, we're given that those opposite sides are parallel. Again, that's by the definition of a parallelogram that we just learned about. Okay, so we have definition of a parallelogram says that those sides are equal. Now, PQS and RSQ, so PQS, oh, my eraser clicked on, PQS and RSQ, those are congruent. And then also PSQ, so PSQ is this angle, and then RQS, this angle here, are also congruent. Now, if we look at what we just did, we said we have parallel lines, and then we have parallel lines cut kind of differently by a transversal, but both of those sets of angles are congruent by alternate interior angles of parallel lines. Okay, and then the reflexive property, again, says something equals itself. Well, it looks like we need to say that side QS is congruent to itself, because if I do that, now I'm going to have some congruent triangles. PQS and RSQ are congruent by the pattern angle, side angle. And lastly, we can say the remaining parts are congruent by corresponding parts of congruent triangles are congruent. Now again, that's the proof of why the opposite sides are always congruent. You're going to see a similar one for opposite angles. I just wanted to go through that proof with you guys to show you that we'll see them again a little bit here and there. So using those opposite sides and opposite angles properties are a little bit more straightforward. If I know the opposite sides are congruent, I look at side AB, and I know side AB has to be congruent to side DC, and now I just plug in. X plus 4 is equal to AB, 12 is equal to DC. Get in a good habit of doing this. Now we can just subtract and solve, and we get X is equal to 8. Okay, for the next one, we have angle A has to be equal to angle C. So angle A is where my variable was Y. Angle C we already know is 65, so we're already done. We just get Y equals 65. So take a moment, pause, try these, find the measures of the indicated values, and then we can move on. So FG, again, FG is opposite HE, so those are equal. So we know FG has to be equal to 8. And then for measure of G, we know angle G has to be equal to angle E, because that's what it's opposite. So we just get E is equal to 60 degrees. Again, we can set these up. So my variable X is at angle J. Angle J has to be equal to angle L. J is equal to 2x. Angle L is equal to 50. We can divide by 2 and solve, and we get X is equal to 25. Y variable is on side LM. I know LM has to be equal to JK because it's opposite. LM is Y plus, not Y equals. Y plus 3 is equal to 18. We subtract 3, and we get Y is equal to 15. Consecutive interior angles we just talked about a little bit ago. We said, again, from chapter 3, consecutive interior angles are supplementary. So we're going to kind of piggyback off of that for theorem 7.5 and say in a parallelogram, if we know these sides are parallel and they're cut by a transversal, and in this case RS is our transversal, we have X and Y are consecutive interior on either side, so we know they have to be supplementary. 7.6, again, you could use any number of things, and we'll prove it here in just a second. But if you have diagonals of a parallelogram, they're actually going to bisect each other. So in order for us to have a parallelogram, all 4 of those things must be true. So opposite sides are congruent. Opposite angles are congruent. We have adjacent angles are sup. And then we have diagonals bisect. So in a parallelogram, all 4 of those things are true given the theorems that we learned about in the lesson. So the proof of the second one, and again, it's pretty easy to set up here. First of all, QRS, PQRS is a parallelogram. We're going to go given. They're going to say PQ is parallel to RS. That's by definition of a parallelogram. Now QPR, so let's mark these. So QPR and then SRP, those are congruent. And then they also said PQS and RSQ are congruent. So again, those are both by alternate interior angles. Parallelogram opposite sides theorem says that those opposite sides are congruent as well, so I'm going to go ahead and mark those. PQ is congruent to RS. And now we can say those 2 triangles are congruent, and this time it's by angle, side angle, if we look at our pattern. And then they just say the rest of those things have to be congruent. So what's given is the theorem that we just proved, that these diagonals have to be bisected and that those segments have to be equal on the inside by CPCTC. And so now we know that M is a bisector, and that's by definition of a bisector. Now that we have that definition of a bisector, again, it's going to give us some problems here where we have to use either the supplementary or the bisector stuff. So it says in this lamp, the measure of angle ADC, which it's hard to see, but it's right there at the bottom, is equal to 110 degrees. And then what it wants us to find is BCD, again, kind of hard to see, but this one right here. Because those are adjacent, we're just going to take 180 minus 110, and we get that has to be 70 degrees. Okay, in our proof here, we just want to prove that angle B is congruent to angle F. So essentially, I need to prove that these two are congruent. All I really need to do is know that those are both parallelograms, though. So if we look at this, it's given that they're parallelograms. Then we say CDA and angle B. So essentially, those are congruent. And then EF and D are congruent. EDG and F are congruent, sorry. The middle step here, again, vertical angles congruent. We can just say CDA is congruent to angle EDG. And essentially, by transitive property, we can get this and get angle B is congruent to angle F. Okay, so kind of a roundabout way. It's pretty easy for us to see, though, that those have to be congruent. Okay, so in example 2, it says, what if BCD, it says find BCD when the measure of angle ADC is twice the measure of BCD. So essentially what they're saying is, if I know BCD, this right here, is twice the measure of ADC right here, we would say 2x, because it's twice the measure, we would say 2x plus x is equal to 180. So we would get 3x equals 180. We would divide by 3, and we would get 60 is equal to x. And that would tell us that the two angles would have to be 120 degrees and 60 degrees for those two angles. And then just for the sake of time in the video, let's not worry about number 4 because I want to get to the coordinate plane ones. You guys can go back and look at that one later, though. All right, so I want to get to these two real quick because they're not super tough, but they do take a little bit of time to graph out. So I'm going to plot the vertices here. Here's L at 1, 4, 7, 4, 3, 4, 5, 6, 7, 2, 3, 4. There's M. N is at 6, 0. And O is at 0, 0. So here's our parallelogram. Okay. Pardon the drawing. It's not super great. Okay. Parallelogram. Just awful. Okay. Coordinates of the diagonal, though. So what I want to do is I want to construct the diagonals here. And when I construct the diagonals, what I have to understand is knowing that how my drawing works, it's going to look pretty awful, but I know that the diagonals are bisected. So one way I could do this, especially if my graph looks like this, is I could do the midpoint formula of one of the diagonals. So that's really all I have to do because they're each bisected. So I'm going to do the midpoint formula for L and N. So I have 1 plus 6 over 2, and then I have 4 plus 0 over 2, which is 7 over 2, comma 4 over 2. And as you can see here, good thing we did this, we get 3.5, comma 2 is the diagonal's bisector, so it's the midpoint. You could have just as easily have done the midpoint there and got the same answer. Okay, this one's a little bit different. If we are given 3 of the vertices, we should be able to find the 4th, and that's a little bit different route, but again, should not be too terribly challenging. So let's write out our vertices. So -1, comma -3. Then we have, -3, comma 2. Let's get that so we can see it. There's x. We have 4, comma -4. So 4, comma -4. This is a good one. Okay. There's z. Okay. So we know that missing vertice is going to be somewhere over here. So essentially, you guys, what we use is the slope. We could do it one of two ways. We could count from W to X and then do the same pattern for Z, or we could go from W to Z and do the same pattern from X. It really doesn't matter. You're just going to use your slope. So I'm just going to go from W to X. I go up 1, 2, 3, 4, 5, and then I go left 2. That means I have to do the same thing here. Up 1, 2, 3, 4, 5, and then I go left 1, 2, and there's where that vertice has to be for that parallelogram. So that's at 2, 1. Okay, so go ahead and pause and try. I know it's kind of hard to see. Go ahead and pause and try those two on graph paper. It's at the back of the room up in that shelf. But those are going to be on your homework. Make sure you have things like that in your notes. That way, if we do ever need to see if we're taking the process the right way and doing the steps the right way, we can earn some points back on quizzes. But have those things handy in your notes for me for when we go back over this. Okay, so if you guys paused, here's what you should have got for your two answers. So I have the midpoint at 2, 3. I didn't write the answer out for this one, but it was 0, 1 on this one as well. But that's how you would find it. You could just use your slope. And again, it doesn't really matter from which point. You just want to use your slope on number 6. The other one, we could do the midpoint formula, or we could just look at the graph if it crosses evenly, and we drew it well. Okay, so hopefully we have the ability to kind of get through our homework now. Again, tomorrow will be a work day. It'll give you guys an opportunity to ask questions. We can go over questions in your notes or questions on the practice set. Thanks, guys. Have a great day.